You can think of your machine learning models as being like high-performance sports cars. So let's say that you trained a model. Think of it as being like a Ferrari. For your Ferrari to have maximum performance, for it to be as fast as it possibly can be, the engine has to be tuned. So it is with your machine learning models. So if you have a particular machine learning algorithm, let's say like a decision tree classifier and a particular data set, it needs to be tuned for that situation at hand. And if you use the decision tree classifier with a different data set, it will need different levels of tuning, different tuning. So the tuning is data set specific. So the process of hyperparameter tuning is all about optimizing your machine learning models for your particular data set at hand. So this hyperparameter tuning crash course is going to focus on decision tree and specifically decision tree classifiers. And the reason for that is simple. We have to have a frame of reference to talk about. But just so you know, at a general level, everything we're talking about in this particular crash course applies to any machine learning algorithm. For example, XGBoost or random forests or GLMNet or whatever it might be. The concepts are exactly the same. The hyperparameter values will differ between algorithms, of course. Every algorithm has different hyperparameters, but the concepts are universal. So I'm going to assume for this crash course that you know two things. First up, I'm going to assume that you know decision trees. And if you don't, no worries. I'll put a card up here to my decision tree machine learning crash course, and that'll teach you everything you need to know. Two, the second thing that I'm going to expect you to know is the bias variance trade-off and cross-validation. Once again, if you don't know that, no worries. I'll put a card up here to my bias variance trade-off video, and it will teach you everything you need. So if you have the requisite knowledge, or if you've watched those two videos, one last thing I want to mention is that if you would like to get the files for this crash course, there'll be a link down below in the description, and I can email you the files so you can follow along. And that's the PDF of all the slides, it's the Python code, and the data. Let's go ahead and get started, and let's talk about why the Python code isn't actually the most important part of hyperparameter tuning. Okay, the first thing I want to establish is this. The Python code to perform hyperparameter tuning is actually the easy part. And here is real life code. We're going to go through this more in depth later on in the crash course here, but take a look. Depending on how you want to count it, this is either 9 or 10 lines of code. That's it. That's all the code that you need to tune a particular machine learning model. In this particular case, we're talking about a decision tree classifier. That's all you need. So the Python code is the easy part. What's most important is actually understanding all of the concepts that underlie the code, if you will, the why. Why are we writing this code in the first place? And the answer is we need to understand the hyperparameter tuning concepts to make sure we understand why we're writing the code that we are. So the first concept that we need to baseline is supervised learning. And if you've watched my other videos, feel free to fast forward this part if you want, or hit one of the video chapters below. So first up, what we're going to be doing is talking about supervised learning in this particular crash course, because there are multiple forms of machine learning, and supervised learning is by far and away the most common in practice used in real world business analytics. So that's why we're going to focus on that. And to really cement some of these ideas that we're talking about, I'm once again going to use a concept that I've used in my previous videos, which is that of a classroom. And in particular, using this metaphor, using this framework, you are the supervisor, you are the teacher. So this is you in this metaphor. You are running the educational experience, if you will. And your student happens to be the machine. So this person right here, it happens to be your student, your laptop, your virtual machine in the cloud, whatever it might be. So you're the teacher, you're supervising the educational process for the machine. And this takes three primary forms at a conceptual level. You have your data, which are your raw materials. You have your algorithm, which is your machine learning technique. And then lastly, you have your training regimen. And when you combine all of these, what you get is a model, a machine learning model. And in Python terms, this is an object. So you can pickle it and save it off as a file and email it to somebody or deploy it to your website, whatever you might want to do. Now, the focus of this particular crash course is not going to be on algorithms and data. We're going to make an assumption about data and we're going to make an assumption about algorithm. Hyperparameter tuning is all about the training regimen. How do you train the model so that it is optimal based on its algorithm and the data at hand? So this is a very, very important part of this Venn diagram here, and this is basically the subject of this particular crash course. With this hypothetical metaphor, this model of supervised learning, applied machine learning is like being a teacher in a classroom. We can also think a little bit about what this means in terms of evaluating the student. Because as the teacher, you want to know, did the student actually learn? Yes or no? And just as with humans, we use testing to do this. So what we do is we take our data, our raw materials, and this right here is going to represent, metaphorically, our entire data set, all the rows and all the columns. And then what we do is we say, okay, in order to be able to evaluate whether or not our model, the computer, actually learned, we need to split the data into two forms. We need to take some of the data and say, look, we're going to use this for training. And in a previous video that I mentioned up here, you can think of this as being like quiz questions and homework questions and that sort of thing that you give to the student to learn. And then you hold some of your questions back, some of your data back, to evaluate at the end of your project or the end of the class, the end of the course, to use the classroom metaphor here. You use this data to actually test how well folks learned. Now I'm going to show you some code here real quick for splitting your data because everyone always asks. And if you choose to get the files below, right? If you choose to get the files below, then you'll get this code. All right, so here's the code. And all I'm doing here is using a built-in data set just to demonstrate what's going on here. It's called the Iris dataset. That was covered in one of my previous videos. And what we want to do here actually is highlight this particular function here, which is the train test split function. This is a very standardized way of splitting your data. And I'm not going to go through this code here because I've covered it in one of my previous videos up here. This is what I really want to talk about. Notice what I'm doing here is I'm doing my train test split. And what I'm doing is I'm passing in my underscore capital X data frame. These are all of my predictors. Or if you're more familiar with statistics, these would be my independent variables. The underscore lowercase y is my labels, the thing that I'm trying to learn how to predict. My label, my target, or in statistics terms, this is my dependent variable, okay? And then I take that raw data and pass it into the function, and then I say, hey, what I would like you to do is take this data and at random split out 20% of it. So I'm going to take 20% and put it in the test set, and the other 80% will be selected at random and put in the training set. And just to be crystal clear, this is all done at random because I know what I just said might not sound like it, but everything's chosen at random. And I'm setting the random state here in this particular function call because if I need reproducibility, if I want to run this code cell in my Jupyter notebook over and over and over again and get the same split every single time, the same random split every single time, I have to set the random state. And I do this in my crash courses for reproducibility. Now, if you don't need reproducibility in your real world work, for example, you're not going to share your Jupyter notebook with anybody, don't worry about it. Then you don't need to set it. But you will get different splits every single time. And what we can see here is the splits. Now, there are 150 total rows in the Iris dataset, so 20% of those rows would be 1/5 or 30 rows. And you can see that right here, 30 rows and 120 rows. So that is the raw code for splitting your data at random. Now, this is also, once again, the easy part, to be quite honest. The real hard part, and I'm sure you're wanting to know, is, Dave, how did you pick 20% of the data being in the test set and 80% of the data being in the training set? And the answer is, it depends on your situation. Your train test splits are very, very complicated. There is no hard and fast rule, 80-20 split, 70-30, 60-40, 50-50 between training and test. There are no hard and fast rules for this. It really depends. So here is a great blog post, and I'll put a link to it down below in the description. And here is a great blog post that you can read to learn more about the factors that you need for determining how much data you need to put in the test set, how much data you need to put in the training set, so on and so forth. Okay, and this also uses Python, by the way, so you'll get Python code here as well. So it's a great, great blog post. Okay, link down below. So now that we've got that out of the way, what I should mention is that in the files, if you choose to get the files that I can email you, then I will provide you a train test split already done using the aforementioned technique that we saw on the previous slide. So you don't need to worry about that, but going forward, you've got these blog post resources if you want to apply these techniques to your own data. It's super important when we talk about hyperparameter tuning to talk about the two forms of supervised learning. These are like the two buckets, the two families, if you will, of the kinds of models that you can build. And in machine learning terms, they come in classification and regression. Now, I have to say, these are computer sciencey terms. If you come from a traditional statistical background, you might be like, Dave, what you're telling me is wrong. And that's totally cool. I get that. But in the machine learning world, these are the common terms that we use. In classification, what we're trying to do is build models that predict labels, categories. So for example, if we're doing fraud detection, is this particular transaction, let's say, fraudulent? Yes or no? That's a label. Another label that we could think of is in the Olympics, bronze, silver, and gold. Bronze, silver, gold. Those are 3 different labels. Okay, so classification is all about predicting labels or categorical information. Regression models predict numeric values. Sometimes these are referred to as targets. And these would be things like weight, price, sales, that sort of thing. Think of something with a decimal point in it, then that's a regression problem. If it's a category, then it's classification. Some machine learning algorithms are either classification or regression. That's all they do. They're specialized. Algorithms based on decision trees can do both. And that's important from hyperparameter tuning perspective because different types of algorithms have different types of parameters. However, when you use decision tree-based algorithms, whether individual decision trees or, for example, the random forest in scikit-learn in Python, the hyperparameter values are exactly the same, whether they're a classification model or a regression model. In scikit-learn in Python, you have, for example, decision tree classifiers, which is what we're going to see today in this particular video, which are obviously classification models. And then you have decision tree regressors, which predict numbers, but the hyperparameters are exactly the same, which makes decision trees a very, very nice place for you to start your hyperparameter tuning journey because the hyperparameter is the same. Real quick, classification, right? It's all categories like I mentioned, but here are some of the business scenarios that you typically see classification models: fraud detection, churn prevention, conversion modeling, underwriting. Classification models are typically the very best place to start your DIY data science journey, your do-it-yourself data science journey, because these types of problems are everywhere and they typically have high business value. So classification is a great place to start. Regression, numbers, right? And business scenarios like marketing mix modeling, price cost modeling, customer lifetime value. Technically, forecasting is a regression problem. Lots of people want to start, quite frankly, their machine learning journey with forecasting. Bad idea. Doing forecasting well using machine learning is extremely valuable. Don't get me wrong. It's probably the best way to do forecasting these days, but it's also the most complicated. And it also typically has the highest risk for you as a DIY data scientist, right? Because forecasting drives really big, important decisions. So I tend to recommend folks early on in their journey, stay away from regression problems if you can, focus more on classification because they are still high value, but they're also stacking the odds of your success. So let's talk about the data. So in this particular crash course, we're going to use a particular data set, which is actually relatively famous in the machine learning community, which is the adult census data set. And you can see here that it was extracted, the data set was extracted from census data from the US Census Bureau in 1994. And the prediction task at hand is pretty simple. You need to use the predictive features, the independent variables, if you're familiar with that terminology, to predict whether or not someone makes greater than 50K a year. This is a classification problem because literally in the data set, there's a string value that says less than or equal to 50K or greater than 50K. So it's a binary state, a 2-state scenario, right? We're trying to predict whether or not someone makes high income or low income, essentially. Now we're going to be using a cleaned subset version of this data set in this crash course. And if you opt for the files, you will get the CSVs. And here's the thing. Like I said, everything that you've learned here is going to be directly transferable to regression. And more generally, the concepts are going to be applicable to any machine learning model. You just need to actually find out what the hyperparameters are and what they do, but the base concepts are all the same. And if you really want to get the actual raw data and take a look at it, here is a link to the actual data sets here. Now here is the metadata dictionary. I'm not going to drain this. Feel free to pause the video if you want and take a look at it. But you can see here we have a bunch of different attributes or variables or features describing US citizens. And then lastly, we have our income label, which is literally this string, less than or equal to 50K or greater than 50K. But you can see here, we can see their age, how much education they have, gender assignment, racial assignment from the US Census Bureau, all that kind of stuff. And we can use these columns here to try and learn how to predict this column. That's what we're talking about. And we want to do it accurately. So we're going to do some hyperparameter tuning to optimize our machine learning model, in this case, a decision tree classifier for this particular scenario. We need to pop up a level. If you've seen my previous videos up here, this will be a little bit of review. Once again, speed up the video or use the chapters to jump to the next section. And what we want to talk about is this concept of under versus overfitting. And the concept of a spectrum is super, super useful for this. So what we can see here is on one side of the equation, we have models that underfit and models that overfit. And the easiest way to think about this is models that underfit leave information on the table. Another way to think about this is in terms of complexity. So models that underfit are typically not complex enough. They haven't learned all of the underlying patterns that exist in the data because they're too simple. They can't learn it all. A model that underfits is very, very simple. And using decision trees as their frame of reference, the simplest decision tree that you can possibly get is what's known as a decision stump, which is essentially just one decision node. That's it. We look at one feature, we check it out, and then we make a prediction based on that one value. Generally speaking, a decision stump is useless in the real world by itself. A single decision stump is usually a terrible model. If it's not a terrible model, your problem was too simple for machine learning. That's the way to think about it. Now, on the other end of the spectrum, we have really super complicated trees, right? This is a much, much more complicated tree than this tree. And we run the danger in machine learning, if we make our models too complex, they become too specialized, if you will, and they overfit. Another way to think about this is that in the extreme case, a machine learning model will memorize the training data set, will memorize every aspect of the training data set, and will look like it does awesome in terms of its predictions because it's memorized the training data set. However, when you put it in the real world and it needs to make predictions on brand new data that it's never seen before, it typically stinks because it's been over specialized to the training data set. So what we want to do is we want to end up in this Goldilocks zone, which means we want our models to be as complex as needed, but no more complex. And this is where hyperparameter tuning comes into play. What we do essentially is we try out a number of different training regimens and we find out which of those training regimens that we tried out have the optimal amount of complexity. And we're going to talk about how you actually evaluate that using real data and real numbers and that sort of thing in this particular video. Okay, so that's what we want. We want to enter in the Goldilocks zone. The easiest way to think about this, once again, is this idea of complexity. What ends up happening is that machine learning algorithms have a collection of hyperparameter values, and these hyperparameter values can be thought of as controlling complexity. Now, once again, we're going to be using decision tree classifiers from scikit-learn and Python as our frame of reference, but the concepts apply to any algorithm, for example, in the scikit-learn library. They all have hyperparameters, and you can go to the documentation and read them and find out what they mean, and then use the techniques that you're going to learn in this crash course to then iterate through all the different types of training regimens for that particular algorithm to get the most optimal outcome. So even though we're going to be talking about specific hyperparameters because we need to, the concept, once again, generalizes. The decision tree classifier in scikit-learn, so this is a decision tree model that predicts categorical labels, supports many hyperparameters. It has a lot. You can go check out the online documentation. However, these in practice are the most useful. In my hands-on work, these are the ones I use. Your mileage may vary, but this is what I use in my own work. So first up, we use max depth. We talk about min sample split, min samples per leaf, min impurity decrease. Now, here are the definitions and here are the default values, but that's a little bit abstract. What's nice is to actually look at different values of each one of these hyperparameters vis-a-vis the same data set and see what their impact is, because that will really build your intuition of how these individual hyperparameters control the complexity of a decision tree. So first up, let's take a look at max depth. Now, max depth is a super, super simple one. By default, it says, look, the tree can grow to be as big and huge as it wants to be. So the default is none, which means the tree can grow very, very large, have many, many levels. But let's take a look at it graphically what this means. So you can see here, using a particular data set, if I set the max depth to 1, I get a decision stump, right? Because the level here is the number of decision nodes, not leafs. So if I want a max depth of 1, I only get one decision node. I get a decision stump. Now, if I get a max depth of 3, reflexively over here, you can see that I get 1, 2, 3, and here are all of my leaves. Now, generally speaking, you're not necessarily guaranteed to get a balanced tree like this, right? You can have a jagged tree even with a max depth of 3. So this just happens to be coincidental. But what this is really telling you is, okay, cool. In a very real way, the max depth parameter is the easiest hyperparameter to understand because it directly maps to the complexity of the tree. The simplest tree in the world has a max depth of 1. This tree is far more complicated. And if I set the max depth to 15 or 20, or I just leave it at none and it grows as big as it wants, then you can see that obviously there's a direct correlation between this hyperparameter value and the complexity of the tree. And you can actually try various values of max depth. We'll see how later on with the code, and then say, which of these is optimal, right? Which of these lands me in the Goldilocks zone? All right, so moving on. The next hyperparameter that is very commonly useful is min samples per split. And what min samples per split says is the number of rows of data that have to be present at a particular point in the tree to allow it to split again. So the easiest way to think about this is looking at these conceptually, right? So when I set my min samples split to 1,000 for the training data set that you will get if you opt for the files, you can see here that the tree gets really, really big, really, really fast. Because what it's saying is if I have a really, really large data set, 1,000 rows being available to do another split to grow the tree one more level isn't that much data. So the tree can get really, really big. I mean, look at this, ridiculously big. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 levels deep over here. Now, notice if I up it to 10,000, I say at any point in the tree, you have to have at least 10,000 rows to do another split. Notice that the tree is far shallower. It's not nearly as deep. It doesn't have nearly as many levels. And once again, complexity, right? This is the way to think about it intuitively. Hyperparameter values allow you to control the complexity of the tree or the complexity of the model, which is more of the general way of thinking about it. So you have different levers at your disposal for controlling complexity. Min samples per leaf. This is related to the last hyperparameter, but actually talks about the number of rows that has to show up in a leaf node. So the easiest way to think about it is, let's look at this guy over here. So I said, hey, the min samples per leaf is 10,000. And notice here that my data set has 32,000 rows total, right? That at the very top of the tree, that's where I start with all of my data, and I have 32,000 rows. And then what you can see here is boop, boop, I do my splits, and notice that these have this node over here has 17,000 and this node has 14,000. If I was going to split again, I have to have at least 10,000 rows in each leaf. And since I don't have enough rows to do that, the tree stops. Now look over here, if I say, hey, min samples per leaf is 1,000, notice I get a far more complicated tree. Kind of very related to the last hyperparameter conceptually. It's just a way of limiting the size of the tree. Now, min impurity decrease is another way to control the complexity of your tree. And instead of concentrating on the number of rows, or what scikit-learn in Python calls samples, we actually focus on, if we do a split, how much better does the tree get? Because what we know from one of these videos up here is that decision trees are trying to minimize the Gini score. And the Gini score essentially is the probability of getting a prediction wrong. So you want that to be as low as possible. So what we'd say here is, look, if we get only just minor improvement, so if we reduce the Gini score by only 0.001, it's okay to do another split, which is a really, really low bar. Now, consequently, if we only have to improve the tree by just a little bit with the split, we get a lot more splits. And then over here, you can see that what I've done is I've actually increased this by quite a bit, right? So instead of 0.001, it's now 0.01. And that's a much higher bar. I notice that my tree is a lot smaller as a consequence. Now, you might be wondering, geez, Dave, which hyperparameters should I use? And the answer is, these four are the most valuable. But in practice, in my experience, I typically only use 2. So take that as you will, right? You can definitely experiment with as many hyperparameters as you would like, but when you're using decision trees, and for example, something like the mighty random forest, which is built on decision trees in scikit-learn and Python, this also applies to that algorithm as well. I typically use these 2. I use min impurity decrease primarily, and then min samples per leaf. Those typically are my go-to. I use both of those at the same time. I try out many different combinations of values. Each combination of values can be thought of as a particular training regimen. And then I compare all the training regimens and find which one works the best. And again, we're going to see that play out in code. Now, let's talk about tuning. Now, this particular section of the crash course is going to assume, once again, that you've watched my bias variance trade-off video, or you're just familiar with the bias variance trade-off in general. Now, what we do is we say, look, we want to map this concept of darts on a dartboard that describe our bias and variance at a very high level to something quote unquote real in Python coding terms. And what we see here is that if we use cross-validation, again, covered up here, we can think of each fold, each validation fold as being mapped to a dart. And I mentioned that in my bias variance video. So let's say, for example, that we're using 10-fold cross-validation, which means we have 10 darts, 10 validation folds, 10 darts at the board. And let's say that we have a set of hyperparameter values. So let's say we're using min samples per leaf and we're using min impurity decrease, and we have a set of values here. Let's say maybe it's 500 and 0.01, okay? And we're using those hyperparameter values, we get these particular accuracy values, let's say, on our dartboard. And generally speaking, if we think of it in terms of accuracy, which is useful for classification models, the bullseye would be 100% accuracy. And what we can see here is that, whoa, yeah, I am exhibiting high bias and high variance here, because not only are my accuracy scores for each validation fold not close to the bullseye, they're far away from the bullseye, but they're also kind of spread out. They're all over the place. So that's high bias and high variance, right? My accuracy score in terms of classification, for example, for each fold in a cross-validation run. Let's say I have another hyperparameter value set, right? So this is one training regimen, right? Because it's one set of hyperparameter values. And then I have another training regimen with a different set of hyperparameter values. And here are my accuracy scores for each of my 10 validation folds. And what we can see here is, relatively speaking, compared to the first scenario, I have high bias but low variance. Because notice that I'm biased, everything's away from the bullseye consistently, but my validation fold accuracy scores, or my darts, if you will, are closer together. Now we can move on to a third hyperparameter value set. This would exhibit low bias and high variance. And then lastly, let's say I've got a fourth value, or a fourth set, or a fourth training regimen. And we can see here, this is low bias and low variance. This idea of running through these different combinations of hyperparameter values is the essence of model tuning. We try different values of hyperparameters, see what's going on, compare them, and pick the one that's the best. Now, to really visualize this, let's take a look at what really happens. Imagine that we're doing 10-fold cross-validations. So we do 10 models, and this corresponds to our hyperparameter set ones. And what you can see here is the accuracy score for each one of the validation folds. Okay, so CV fold 1, validation fold 1, I got 80%, 89%, right? Notice there's some variance here because the numbers are all different. So what we do to actually really solidify, to really make these ideas concrete, is to use some mathematical calculations. So for example, when I'm only using 10-fold cross-validation, some reasonable metrics to embody bias and variance are the mean, or the average, and the range. So on average, if I take all of these accuracy scores, on average, my mean accuracy score was 84.5. And once again, remember, a bullseye, using our dartboard analogy, is 100% accuracy. So this is my bias, and my variance is the range. And the reason why I'm using the range is because I only have 10 darts. Using a more sophisticated idea of variance is probably not a great idea to use with only 10 data points. So the range is simply the highest value minus the lowest value, and that's the range. And it's an idea of how far apart are my values. And once again, not surprisingly, these map to this idea of bias and variance. Now, this becomes a mathematical way for me to compare, or for you to compare, one set of hyperparameter values to another during the tuning process. So imagine if I have my hyperparameter set 2, which we saw graphically on the last slide represented by darts on a dartboard. But let's say my bias is 85.35 and my range is 2.2. Now notice that this set of hyperparameters is better than this based on these 10 data points, based on 10-fold cross-validation. Because notice that my bias is less. Because remember, my mean score increases, it gets closer to 100%, the better, right? The bullseye is 100% using the dartboard metaphor. And notice that the range is far smaller than it is over here. That's awesome. And what that means is that not only am I getting closer to the bullseye on average, but I'm also getting a much closer spread of my darts. So this hyperparameter value set, this training regimen, is better than this one. Not based on opinion, not based on interpretation, based on math. We can keep going. We can say, okay, here's hyperparameter value set 3. Well, this is a bit of a trade-off. Notice that my bias has gotten better. My bias is lower because I'm getting closer to the bullseye, closer to 100% accuracy on average. Unfortunately, my range has grown, which means that my darts are way, way out of whack. So this number actually isn't necessarily all that representative of what we might expect in the real world, because notice that in this data set, I've got as low as 84.3. I think that's the lowest value. Yeah, that's the lowest value. So if I just relied on this, I'd be like, man, that's a really good model. And then you go over here and be like, wait a second, but sometimes it's scored 84%. That's not so great. So range, a big range tells us that our expected predictive performance can be kind of wild. So what we want is both a high mean and a low range simultaneously. And now, of course, based on what we saw in the previous slide, the fourth parameter set is actually the best, because not only does it give us the lowest bias, that is the closest to the bullseye, but it also gives us the most densely packed set of darts. Now, this is all super important because what we're doing here is not only optimizing our machine learning models for our data set at hand, but also trying to get an estimate of how well our machine learning models will perform once they're out in the real world and brand new data that they've never seen before comes into play. Because what we want to do as DIY data scientists is say, look, if I actually make business decisions using this machine learning model, what kind of performance, what kind of accuracy, if you will, should I expect over the long term in general? And we want that, because if we can't get that score, that estimate to be good enough to meet our business requirements, then we shouldn't put the machine learning model in place to do any sort of business process decisions. That would just be a bad idea. So we need some sort of way of estimating this. And that's what we use our tuning for. Now, in the case of this particular set of 4 hyperparameter value sets or training regimens, this is obviously the winner because it gives us simultaneously the best average predictive performance with also the least amount of variance. So we can go to our boss and say, in theory, hey, yeah, I've built a machine learning model. It's 95% accurate. And generally speaking, we should expect it to give us between 93 and 97% accuracy. That's what we're trying to get at. Okay, that's the whole point of hyperparameter tuning, is to understand the performance and also the general and understand how it would generalize to new and unseen data. Real quick, I need to mention the test holdout set with hyperparameter tuning. This is super, super important. The test holdout set cannot be used or influence your training at all in any shape or form, or it is useless. And here's the reason why. The test holdout set is your final estimate of generalization error. So the way your project works in general, and you can see here, I've listed it out by step, but at a high level, this is the way it works. You grab your data. The very first thing that you do is you split it. So let's say you pull from a database. First thing you do is you pull your data from your database and you split it. You don't look at it. You don't analyze it. You don't visualize it. You don't do anything like that. You split it at random. And then you say, this is my test data set, and I lock it away in a safe. I'm never going to look at it until the very end of the project. And then you just work with the training data. Now, using the classroom analogy, again, the way you can think about the test holdout set is like a university course. So when I was an undergrad, many, many years ago, I had a professor who basically said, I don't care if you come to lecture. I don't care if you read the textbook. I don't care if you do the homework. Don't care, don't care, don't care. 100% of your grade is based on the final exam at the end of the course. That's the way to think about the test holdout set. You use it once and only once. That's all you use it for, because it's like that final exam. And this is basically the process that you use, right? So you spend most of your time iterating over the training data set, including your hyperparameter values. And then once you've found your hyperparameter values, you use that final model with the best hyperparameter values that you've found, and then run it against the test data set. And then that test data set becomes your final exam. How well is my model going to do? And ideally, what's going to happen is that you're going to create estimates using hyperparameter tuning for your bias and variance. And then once you run your model against the test data set, the value that you get out of the test data set, the accuracy score, for example, should align with your estimates. And when it does, that is a very, very powerful indication that you have created a useful model that can help your business be more successful. Here's the thing to remember, though, and a lot of people don't like this, but I got to say it. There is no guarantee at the beginning of your project that you're going to craft a useful model. Now, when I teach this course, when I teach machine learning at Live, I get a lot of frowny faces in the classroom when I mention this, because most organizations don't work this way. You ask for some budget and they expect something in return. The problem with machine learning is if your problem is non-trivial in terms of difficulty, you actually don't know up front if you're going to be able to build a useful model. You have to try. And this is the process that you use to try. Maybe you'll come up with a useful model, maybe you won't. But got to keep this in the back of your mind that there is no guarantee at the beginning of your project. So those are all the concepts. That's super, super important. All the concepts that you need. So let's talk about how we actually implement these in Python. And I'm not going to drain all of this code. I'm going to just briefly go through some of it because once again, I'm going to assume that you're familiar with these videos up here. So first up, the code, if you choose to get the code, you have me email you the code. What you'll see here is I'm loading up the training file. And remember, I've already done the train test split for you already. And you can see the various features here, just like we saw on the metadata dictionary for the data set way before. So we load this up as a CSV file from a CSV file. Then we set everything up. So we're going to use a one-hot encoder to actually encode our categorical variables as ones and zeros. Once again, check out the videos up here. And I'm going to use these numeric features and these categorical features. So I'm only going to use a subset of features in the model. And I'm going to also transform one of the, actually I'm going to engineer a feature, I should say. So what I'm going to do is I'm going to take the string values of male and female, which are in the sex feature of the original data set, and then replace them with ones and zeros, and then store that in the female feature, which I'm including up here, because this is actually a better representation. Because the US Census Bureau data set has set up gender as a binary indicator. So that's what we're doing here. And then we one-hot encode everything. Again, check out the video up here. If you do watch my video up here, I use pandas to do this. This is another way of doing it. And technically, this is probably a better way of doing it, is to use the one-hot encoder. And then all I do is one-hot encode my features and then combine my numeric features and my one-hot encoded features into a data frame, which I call train_X. So these are my features or independent variables for my model. And you can see here that these features remain unchanged, right? They're numeric. Then over here, you can see my one-hot encoded features, marital status divorced, so on and so forth. We're also going to use the label encoder. This is no different than the video up here because we have string values of less than or equal to 50K and greater than 50K. We have to transform them into numeric values for scikit-learn. And what we can see here is that less than or equal to 50K maps to 0 and greater than 50K maps to 1. Now, with all that in place, we can actually do some model tuning. Let's just take a second here and just walk through this, okay? Because this is the meat of the crash course in terms of how you actually do everything we just talked about. All right, so first up, we're going to use an algorithm. In this case, we're using a decision tree classifier. And then from the model selection module of the scikit-learn library, I'm going to pull in repeated cross-validation fold and grid search. And this will make a little bit more sense as we walk through this. So first up, I need to define the hyperparameters that I want to tune and all the various values of those hyperparameters that I want to try out. So you can see here, I'm using my two favorites for decision tree classifiers, min samples per leaf and min impurity decrease. And I'm saying, hey, I would like to try out 25, 50, 75, 100, 200, 300. I would like to try out 0, 0.001, 0.005, so on and so forth. And what I would like to do is try out every single combination. That's what I want to do. This is what's known as a grid search. So I have 1, 2, 3, 4, 5, 6 values, 1, 2, 3, 4, 5, 6 values. So there are 36, 6 times 6, or 36 combinations. And I want to try out all 36 combinations and find out which one works the best, which one gives me the highest accuracy. I set up a dictionary. So this is a Python dictionary, right? Here's my dictionary key, my values as a list, and I'm calling this my parameter grid. You can call it anything you want, but this is pretty standard naming convention, so parameter grid. I instantiate my decision tree object, and notice I'm setting the random state here simply because if you run the code that I can send you, I want you to see pretty much the same thing that you're seeing right here. So I set the random state, and then I'm doing repeated k-fold cross-validation. Now this is super important. On a previous slide, to keep things simple, I used 10-fold cross-validation, where I get 10 darts for my dartboard. In general, that's not bad, but it's kind of the gold standard if you can to actually run 10-fold cross-validation repeated 10 times. So 10 times 10 is 100, or 100 darts at the dartboard. And then when you use 100 darts, you get a much better estimate of both your bias and variance. So that's what I'm doing here. So I'm doing 10 splits repeated 10 times. So Tenfold cross-validation repeated 10 times. 10 times 10 is 100. And again, I'm using a random state here, 5, 4, 3, 2, 1, totally arbitrary number, simply because if you run the code that I can send you, I want you to see basically the same thing, if at all possible. Okay, and the only way to do that is to set the random state. Now we're ready to do our grid search. And what I want to do here is I want to set everything up to say, okay, look, I want you to go through all 36 of these parameter value combinations and evaluate them with tenfold cross-validation repeated 10 times. So basically what I'm doing here is I'm saying, okay, I have 36 parameter combinations, which each one I have to try out. So that means I have to do 36 runs at base, 36 cross-validation runs. And then simultaneously, I'm saying each cross-validation run actually is tenfold cross-validation repeated 10 times, or 100 folds. 36 times 100 gives me 3,600 models that are being trained. Because remember from the video up here, every fold requires you to train a model. And if I have 100 folds, that's 100 models, 36 combinations, because I have 3,600 models. So here's the thing you need to know about hyperparameter tuning. It typically takes a really long time. It's very compute and memory intensive. It can take a very, very long time, especially if you use tenfold cross-validation repeated 10 times, which by the way, I would highly recommend that you do. So what you can see here is I'm setting in my grid search object here, grid search CV for cross-validation. I'm passing in my algorithm, which happens to be a decision tree classifier. I'm passing in my parameter grid. And then I'm saying, hey, how you evaluate everything is by using accuracy. And there are various types of scoring metrics that you can use beyond accuracy. But since we're using a classifier here, we're going to use accuracy, which is pretty standard. And then njob says, look, I can actually do this in parallel. I can do this work in parallel. Every fold can be treated separately. So if you have a really powerful computer with lots of cores or lots of CPUs, you can actually set this job and it will run faster because it'll do multiple things in parallel. Now be super careful. If you're using your work laptop, for example, not only do you need to worry about the number of cores, how much CPU you're using, but also how much memory you have. So typically you want to be really, really careful of this value. Generally speaking, one of the best options is to run this on a cloud VM. Like you just spin up a VM and it could be really, really beefy and you run this stuff and then you shut it down when you're done. But if you don't have that option, you can still use your laptop. I also pass in my cross-validation specification here because notice my object here is called CV. This is my tenfold cross-validation repeated 10 times. Boop. And then refit equals true says, look, this is what I want you to do. I want you to go through all the hyperparameter values, do tenfold cross-validation, and when you find the best set of parameters based on accuracy, train me one final model with all of the training data, not using tenfold cross-validation, but all the training data with the best hyperparameter values. And that'll give you one last model that is essentially tuned. That's what this means, refit. So then I say, okay, cool, I create my object, I call it grid CV, I then feed it my training data and my labels, and then I ask it to fit. Scikit-learn, this naming convention in scikit-learn says, look, fit means go learn, go do the work. So go do the work. And this will take a long time to run. It will take a long time to run because we're making 3,600 decision trees. It takes a while. And then once it's done chunking away, we can then ask it, hey, grid search, what were the best parameters? So this is attribute of the object that is populated after you call fit. It's found out which of them are the best based on accuracy. And it says, hey, Dave, based on these 36 values of hyperparameters using the decision tree classifier and the data set that you gave me, the best set of hyperparameters are min impurity decrease is 0. So just split. Doesn't really matter how good the split is. Doesn't matter. Very low bar for the split quality. And the min samples per leaf is 100. So notice that it picked this value out of the 30, out of this 6, and it picked this value, or this particular one combination out of 36. And that's awesome. That's good to know. However, what we really want to do, though, to be really awesome with our machine learning, we want to actually map this whole process to the bias and variance. We want the estimates, right? So this is how we do that. So here's the code. What we can do here is pull back the CV results from our grid search object. And then we can turn that into a data frame because data frames are just easier to work with. So we're going to turn that into a data frame. And then once we do that, we're going to say, look, we don't want everything out of the data frame. We don't want everything out of the data frame. What we want is just the aspects of the CV results that are related to the splits. So splits is synonymous with folds, right? So we want to go look at every one of the 100 folds. And what we're going to get back here in this CV results data frame is essentially 36 rows. That's what this data frame will have, 36 rows. And each one of those 36 rows, of course, corresponds to a particular combination of hyperparameter values. And then what we get back are 100 split columns, right? Because we had 10-fold cross-validation repeated 10 times, so we'll have 100 columns with 100 accuracy scores for each of the 36 rows. That's all of our data, right? So for this particular value of hyperparameters, these were the accuracy scores across the board for all 100 splits or folds. Sweet. So once we get that data frame, we can then ask for just the row. Remember, there's 36 rows. We want just the one row that is the best index. So this number right here comes back from our grid CV. We use loc to grab it. So we want to grab just this row, right? This is the row of the best hyperparameter values. And then we want all the columns. And then we get our best results. And then all we have to do, because this will come back, I believe is a pandas series object, if I remember correctly. We just ask, hey, give me the mean. Because what I'll have is a row, which can be treated as a series object in pandas. I'll have a row with 100 accuracy values for the single best hyperparameter combination. And then I can just say, hey, on average, what was my bias? So I just call the mean on it. And you can see here that my estimate for the best hyperparameter values using 100 folds is, on average, I would expect this set of hyperparameter values to give me a model that is around 81.7% accurate. Now, next up, we need to get our variance, because this number alone is not enough, because we want to know how wildly could our predictions vary in the real world if we decide to use this model in some sort of production scenario. So what we want to do is estimate our variance, and we can use standard deviation now because we have so many more data points. And what we're doing, and if this doesn't make sense to you, don't worry about it, but I'm going to say it for folks that might be interested. We're assuming a normal distribution here for our calculation here, but we're going to use the standard deviation. And in practice, this works out quite well. So I just say, hey, look, of the 100 values, what's the standard deviation? Now, if you're not familiar with the standard deviation, I'm not going to go into it. The easiest way to think about it is using a rule known as like 66, 95, 98, as I recall. What this is saying is that the standard deviation as a accuracy metric, because remember, this is accuracy. So our standard deviation is about, call it about 1%, right? Because if we lop off these two zeros, it's 0.95%. Well, that's close enough to be 1. So we'll call it 1%. So what this is telling us at very high level terms is that one standard deviation will represent what the prediction scores will be about 66% of the time, about 2/3 of the time, okay? So plus or minus 1%. So hey, boss, my bias estimate is about 81.7%, and about 2/3 of the time, the model should range between 80.7% and 82.7%, because that's one standard deviation. Now, 95% would be 2 standard deviations. Hey, boss, my model is estimated to be 81.7% accurate. 95% of the time, it's going to be between 79.7% accurate and 83.7% accurate. That's how you should think about standard deviation. And then, of course, 3 standard deviations is like 98%, something like that, right? Most of the time, you usually just rely on two standard deviations. It's pretty good in practice, okay? So 95% of the time, we would expect this model to have an accuracy between 79.7 and 83.7%, okay? Now, here's the thing. Now we have our accuracy estimate. When we do the final testing, the final exam, we would want our results to fall within that estimate, 79.7 to 82.7%, 83.7%, excuse me. That's our bounded range. And if our test set accuracy is within that range, it's a really, really good sign that you can hang your hat on that model performance going forward. And if it meets your business requirements, good to go. And if it doesn't, there you go. That's the unfortunate side of the equation. So let's talk about how we do the testing. So let's assume that we've gone through our entire project, blah, 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 and we're ready to do final testing. What we need to do is prepare the data. So what we need to do is load up our test data set. We need to create the female feature on it, just like we did with the training data set. And then we can just reuse our feature list objects, from before. And we can do things like encode our categorical features using the one-hot encoder that we built before, which is why it's typically better than using pandas. And then we can also concatenate just like we saw before. And if I run head, you can see, yep, Everything looks the same. We'll have all the same columns between the training and test set. That's absolutely required to actually run predictions. We'll also create our labels for the test data set. Using our label encoder, we'll just reuse it. The transform method in scikit-learn is a naming convention. Transform says, look, use what you've learned and apply it. So use what you've learned before and apply it to the labels of the test data set. And we get back the same mappings here. And then we're ready to do our model testing. So what we can do here is we can go back to our grid CV object and say, give me the best estimator. That's where the refit equals true parameter comes into play. It says, hey, do one last go around and train one last decision tree on all the training data with the best hyperparameter values. And that comes back in the attribute known as best estimator. And I can say, hey, what is the type? And you can see here that in fact, it's a decision tree classifier. Yay. And then we can run the decision tree classifier, right? The best tree, right? The tree was trained with all the data on the best hyperparameter values. And we can say, hey, score yourself against the test data set predictors, test data set features, and the labels, and give me back what the accuracy was. Go make your predictions and tell me how good you are at it. And notice what comes back. The test accuracy comes back as 81.3%. Yes, right? Because remember, our mean estimate of accuracy was 81.7, and we're at 81.3. So we're like real close. This is a very, very good indication that if you put this model into production against future U.S. Census Bureau data with the same features, right? We got to make sure that everything lines up. It's got to be the same. That we would predict that in general, we can predict income level with around 81.3% accuracy going forward, and which aligns with our hyperparameter estimates. And this is the secret. This is the final secret sauce for making your DIY data science skills super valuable to your employer. All right, so to wrap up, if you're interested in continuing your learning, here are some more blog posts from Machine Learning Mastery. I have no affiliation with this particular blog at all. It's just got a lot of good stuff on it. So there'll be links down below in the description for that. All right, so that's it for this video. The next video in my series is going to cover the 6 top machine learning techniques that you need for DIY data science, right? These basically are the 6 that basically I've needed for like 80 to 90% of my real world data science work over the years. So that video will be coming up next week at the time of this recording. And when it's ready, it'll show up as a tile here on the screen. Otherwise, I'll put another one of my videos on there in the meantime, in case you might want to watch that video. Okay, so please stay healthy, and I wish you very happy data sleuthing.